What if the universe, your thoughts, your body, the stars, the void between them, was a fleeting sketch on a cosmic canvas poised to be erased? What if reality, vast and ancient, rested on a delicate thread, ready to snap without warning? In the eerie realm of quantum mechanics, this isn't mere fantasy. Our universe may exist in a false vacuum, a fragile state teetering on collapse. A single quantum flicker at any moment could unleash a wave that rewrites existence at light speed. No explosion, no sound, just instant transformation. Atoms would unravel, time and space would dissolve, and reality as we know it would cease. You wouldn't feel it. You wouldn't see it. It would simply be. This isn't science fiction. It's a chilling possibility rooted in quantum tunneling, where the impossible becomes probable over cosmic time. Join us as we explore vacuum decay, the Higgs field's hidden role, the multiverse's fate, and the profound questions of a reality that might vanish. This is a descent into science's deepest uncertainty, a journey that could redefine everything. You wake up to a normal day, sunlight, sky, routine. But far away, reality begins to fail. A silent, unstoppable ripple spreads, an end with no warning. No sound. Just nothing. This isn't sci-fi. It's the false vacuum hypothesis, where the universe hides a fragile, cosmic lie. Every theory of physics, from Einstein's elegant equations to the bizarre truths of quantum mechanics, is held together by assumptions we've never truly tested at the edge. We trust space and time to behave. We rely on particles to act the same way today as they did yesterday. But what happens if reality decides to shift? What happens if the foundation itself begins to dissolve? In the silence of deep space, quantum fields tremble with potential. Invisible particles blink in and out of existence, hinting at a deeper chaos beneath the order we perceive. Black holes whisper secrets we can't yet decode, secrets that might one day burst forth and rewrite the very architecture of existence. The boundary between what we know and what we think we know is razor thin, and we're starting to see cracks. The James Webb Space Telescope peers farther into the past than anything before it, revealing galaxies that shouldn't exist, behaving in ways that challenge every cosmological model we've ever built. Quantum computers, running trillions of calculations a second, sometimes produce answers that defy classical logic. Are we glimpsing a deeper structure of reality? Or is the structure itself beginning to glitch? The universe doesn't owe us consistency. It has never promised to behave in a way that fits our theories. If the very fabric of space-time is woven by something even stranger than strings or particles, if consciousness, entropy, or information lies at the core, then pulling on the wrong thread could unravel everything we know. This is the moment we find ourselves in, not just standing at the frontier of physics, but at the precipice of a reality that may no longer be stable. Every breakthrough peels back a layer, but what if one more layer down lies not truth, but collapse? The cosmic cliff is not just theoretical. It's a possibility so wild, so fundamentally unnerving, that even the most brilliant minds hesitate to name it out loud. The idea that reality might not just be misunderstood, it might be on the verge of breaking. And if that cliff gives way, there's no telling what's waiting in the void. When we hear the word vacuum, we tend to think of emptiness, a space devoid of matter, a void where nothing happens. But in quantum physics, a vacuum is anything but empty. It's a seething ocean of invisible energy, pulsing with ghost particles, virtual interactions, and raw potential. At every point in the universe, even the darkest corner between galaxies, space is never truly still. It's alive with invisible motion. And that reality is far stranger and far more dangerous than anyone ever imagined. To understand this, we need to step into the world of quantum fields. These are not just abstract ideas, they are the fundamental ingredients of the universe. Everything, electrons, photons, quarks, is not made of matter in the traditional sense, but emerges as a ripple, a vibration, a temporary excitation in a deeper field that fills all of space. Think of a calm ocean. Now, imagine a single wave rising from its surface. That wave is a particle. But the ocean, that's the field, and it's everywhere. Every type of particle is tied to its own field. An electron isn't a tiny object flying through space. It's a disturbance in the electron field. Photons, ripples in the electromagnetic field. Even the infamous Higgs boson is just a brief swell in the omnipresent Higgs field, which gives mass to other particles. The vacuum, then, is what we get when all these fields are in their lowest energy state, when no particles are actively being excited, but it's not calm. It's foaming, flickering, jittering with possibility. This is where things start to get unsettling. Because physicists have long suspected that our vacuum, the one our entire universe floats within, might not be the true vacuum. It might be a false vacuum. That term, though technical, is chilling. It means the vacuum we live in is stable for now, but not truly stable. It's metastable, balanced like a pencil standing on its tip. It could stay that way for 1 billion years. Or it could fall in the next second. The idea comes from quantum field theory itself. Many potential configurations exist for how fields arrange themselves. Some are lower in energy than others, like valleys of different depths in a mountainous landscape. Right now, all the fields in our universe might be sitting in a shallow valley, a local minimum, thinking they found their most comfortable state. But what if, hidden beyond some energetic barrier, lies a deeper valley? A true vacuum, a lower energy state, a more fundamental version of reality. If our universe were to tunnel into that deeper valley, a process known as quantum tunneling, it would trigger a vacuum decay event. A bubble of true vacuum would appear somewhere in space, instantly expanding at the speed of light. Inside this bubble, the laws of physics as we know them would cease to exist. Constants would change. Forces would warp. Atoms might not even be able to form. Everything we are and know would be annihilated, not through fire or explosion, but through a shift in the very logic that keeps matter together. This isn't a fantasy. The mathematics of quantum field theory allows it. In fact, some calculations involving the Higgs boson suggest that we might already be living in such a precarious state. The mass of the Higgs, about 125 giga-electronvolts, is eerily close to the value predicted if we were perched in a false vacuum. It's like nature is whispering to us, "You're not supposed to be here." What keeps us safe? for now, is the vastness of energy needed to breach the barrier into the true vacuum. Quantum tunneling is incredibly rare over large distances and high barriers. But it's not impossible. It just takes one random fluctuation, one quantum twitch to tip the balance. Or worse, a high-energy event like the collision of cosmic rays or the impact of a sufficiently powerful particle accelerator to push us over the edge. That's why the term fragile balance isn't poetic exaggeration. It's a literal description of our universe's foundation. Everything we do, every scientific experiment, every second we exist relies on a false sense of permanence. And yet, the vacuum beneath our feet may be temporary, a phase of reality that could change without warning. Even more fascinating is how this delicate vacuum structure might be tied to the early universe. Right after the Big Bang, the universe expanded rapidly in an event known as inflation. This inflation is thought to have been driven by a high-energy vacuum state. When that state decayed, it released the energy that formed all matter, stars, and galaxies. In other words, vacuum decay created everything. But what it giveth, it could taketh away. And there's another twist. Some physicists now believe that other regions of the cosmos might already exist in that true vacuum, alternate pockets of reality sealed off by their own bubbles of different physics. These bubble universes would be unreachable and utterly alien. We wouldn't even know if one was heading toward us until the moment it arrived, rewriting existence in its wake. The vacuum is not empty. It is the deepest kind of fullness, charged with rules, forces, and hidden truths. And it's not guaranteed to last. We walk on a cosmic surface tension, unaware of how thin the membrane truly is. One fluctuation, one transition, and it could all change. And if that change comes, we won't see it coming. There will be no warning, no alarm, no escape. Just the silent birth of a new universe and the sudden erasure of ours. There's something profoundly unsettling about the notion that the universe could disappear without warning. No build-up, no countdown, no final moment to make peace. Just existence, wiped clean in an instant. This isn't the plot of a sci-fi movie. It's a real possibility baked into the equations of quantum field theory. At the heart of this nightmare scenario is a process so calm, so silent, and yet so fatal, it almost defies comprehension. It's called vacuum decay, and the force behind it is a bubble, one so small, so fast, and so destructive that if it forms, it will be the last thing the universe ever knows. To understand how this bubble could end everything, we need to revisit the concept of a false vacuum. Think of it like a marble sitting in a dimple on a hillside. It's nestled in a shallow valley, stable enough to stay put. But if there's a deeper valley nearby, just over a hill, the marble could, in theory, roll down to that lower state. In the same way, the vacuum of our universe, the energy state of empty space, might not be in its true lowest energy form. It could be stuck in a local minimum like that marble, stable for now, but not forever. Here's where it gets terrifying. In quantum mechanics, systems aren't strictly bound by the limits of classical energy. Thanks to a phenomenon known as quantum tunneling, particles, and indeed fields, can spontaneously move through barriers that would otherwise trap them. It's as though the marble occasionally, without warning, disappears from its shallow valley and rematerializes in a deeper one. In the context of the universe, this means the vacuum itself could suddenly decay. One moment, space is as we know it. The next, a tiny bubble of lower energy vacuum pops into existence anywhere at any time. This bubble would be surrounded by a thin wall where the false vacuum transitions to the true vacuum. Inside, the laws of physics are rewritten. Forces behave differently. Fundamental constants like the speed of light or the strength of gravity might shift. The particles that make up atoms, protons, neutrons, electrons may become unstable or cease to exist altogether. Chemistry would stop. Life would be impossible. Matter itself could dissolve into unfamiliar components. The process is not explosive in the cinematic sense. There's no fiery shockwave, no mushroom cloud. It's far worse. The bubble expands at the speed of light, meaning nothing can outrun it. No signal could escape to warn distant observers. There's no place to hide, no force to resist it. You wouldn't see it coming because it would reach you before photons from its edge could even hit your eyes. Theoretically, this transition would begin in an infinitesimal region, smaller than a subatomic particle. Within a fraction of a second, it would balloon outward, converting everything in its path into a new kind of reality. From its center, it would stretch across galaxies, devouring stars, planets, dark matter, even space-time itself. It wouldn't just kill the universe, it would overwrite it. What's more chilling is that this isn't just a hypothetical possibility. It's a mathematically allowed feature of our best physical models. When researchers calculated the implications of the Higgs boson's mass after its discovery in 2012, many noticed something disturbing. The measured mass places us very close to the boundary between stability and metastability in the Higgs field. We're not clearly in the safe zone. Instead, we seem to be sitting uncomfortably close to the tipping point. According to some models, our vacuum is stable enough to last for billions of years, but not guaranteed to do so. One fluctuation, one moment of extreme energy, and it could decay. Could a high-energy particle collision, like those produced in the Large Hadron Collider, trigger such a transition? That question sparked global debate. The consensus among physicists is that Earth-based experiments are far too weak to pose such a risk. Cosmic rays from deep space smash into our atmosphere with energies far exceeding anything we can produce, and they'd been doing so for billions of years. If vacuum decay could be triggered that easily, we probably wouldn't be here to worry about it. But that's not a comfort, because quantum tunneling doesn't require a push. It doesn't care about time or place. It can happen spontaneously, governed only by probability. The longer the universe exists, the more likely it is that such an event could eventually occur. It's like playing Russian roulette with the cosmos. Only the gun has a near infinite number of chambers, and every tick of the universal clock is a pull of the trigger. Inside the bubble of true vacuum, everything is alien. Physicists suspect it wouldn't be empty per se, but rather structured according to different rules. Particles might not exist in the form we recognize. Space might curve or ripple in completely new ways. If time exists at all, it could move differently, backward, sideways, or not at all. The symmetry of physical laws might be unrecognizable. It would be, essentially, a new universe, one that obliterated the old to make room. And yet, there's an almost poetic irony to this idea. The same mechanism that might end our universe could also be how it began. Cosmologists believe the Big Bang may have started as a kind of vacuum decay, releasing an unimaginable burst of energy and creating a universe teeming with structure and complexity. Vacuum bubbles, then, are not just destroyers. They're creators too. They rewrite reality, both ending and beginning in the same breath. It's even possible that our universe is just one bubble among many, spawned from a decaying vacuum in a larger multiverse. If that's the case, then countless other bubbles may already exist, each with its own rules, its own time, its own matter and minds. Perhaps, somewhere in the void, another bubble is expanding now, headed our way. Perhaps its edge will pass through us in 1 billion years, or tomorrow. But this isn't a horror story meant to induce fear. It's a story about humility. The universe does not operate according to our expectations. We may never fully understand the architecture of the vacuum, nor predict when or how it might shift. But we can appreciate the sheer strangeness of existing at all, balanced on a thin thread of temporary physics, wrapped in laws that might one day vanish. For now, the bubble hasn't formed. The vacuum holds, and reality, fragile, flickering, and utterly miraculous, continues on. When scientists at large, Hadron Collider, announced the discovery of the Higgs boson in 2012, the moment was met with global celebration. It was the missing cornerstone of the standard model of particle physics, a key predicted component that had eluded confirmation for nearly half a century. But behind the champagne and applause was an unsettling whisper from the universe itself, one that grew louder as physicists crunched the numbers. Because buried in the mass of the Higgs boson was a potential warning sign that reality, as we know it, may be more fragile than anyone had hoped. To understand the Higgs field and its troubling implications, we must first grasp what it is and why it matters so much. In the quantum world, every fundamental particle is associated with a field. Electrons, for example, come from the electron field. Photons are excitations of the electromagnetic field. These fields permeate all of space and determine how particles behave. But the Higgs field is different. It's not just responsible for one particle. It gives mass to all massive particles in the universe. In the earliest moments after the Big Bang, the universe was in a high-energy, chaotic state where particles had no mass. They zipped around at the speed of light, colliding in wild, unstructured interactions. Then, a phase transition occurred. The Higgs field turned on, bathing the universe in an invisible energy sea. As particles interacted with this field, they acquired inertia, what we perceive as mass. Some interacted strongly, like the double U and Z bosons, becoming heavy. Others, like photons, didn't interact at all and remain massless. This cosmic phase change was the universe's first brushstroke toward structure. Mass meant that particles could slow down, clump together, and eventually form atoms, stars, planets, and life. Without the Higgs field, the universe would be a cold, featureless soup of light-speed particles and nothing else. In this sense, the Higgs field is more than a scientific curiosity. It's a foundation of reality. But here's where it gets strange. When scientists measured the mass of the Higgs boson, about 125 billion electron volts, GeV, they realized something wasn't adding up. In a stable universe, you'd expect that mass to correspond with a vacuum state at the very bottom of the energy landscape, the true vacuum, where the field is resting comfortably in its lowest possible energy. Instead, what they found suggests that our universe may be sitting in a metastable state, like a ball resting in a shallow valley with a deeper one nearby. This means the vacuum of space might not be truly stable. Instead, it's like a thin sheet of ice stretched across a deep lake. It's holding for now, but a sudden fluctuation, a quantum nudge, could cause the Higgs field to slip into a more stable state, changing the entire energy profile of space itself. This is what physicists refer to as vacuum decay, a transition from our false vacuum to a true vacuum triggered by the Higgs field falling into that lower energy minimum. Why is the Higgs mass so concerning? It's not just the value itself, but how it relates to other constants in the Standard Model. Physicists run simulations using what are called renormalization group equations to project how these constants change at higher energies, like those present in the early universe. When they plug in the known masses of the Higgs boson and the top quark, the heaviest known elementary particle, they find something chilling. The numbers suggest that the Higgs potential dips negative at extremely high energies. This creates a true vacuum, well far below our current state, implying that while our current universe feels stable, it might just be temporarily perched on an energy plateau. In practical terms, this suggests we live in a universe balanced on a knife's edge. Any significant disturbance, an extreme fluctuation, a rare high-energy event, could push the Higgs field into that deeper vacuum. And once it starts, the shift would be unstoppable. A bubble of the new vacuum would expand at the speed of light, altering the laws of physics as it passes, obliterating all existing structures. The fact that we haven't observed such an event suggests two possibilities. Either the universe is more stable than we think, and our equations are missing something, perhaps unknown physics that kicks in at higher energies. Or, more disturbingly, we simply haven't waited long enough. The timescale for such a decay could be unimaginably long, longer than the current age of the universe. That's comforting on the surface, but only if the probabilities don't shift unexpectedly. This mystery has led physicists to propose several ideas. Some believe that physics beyond the Standard Model, like supersymmetry or extra dimensions, might stabilize the Higgs potential, flattening out the dangerous dip. Others propose that the inflationary period of the early universe, a rapid expansion driven by high energy fields, might have pushed the Higgs safely into its current state. Still others argue that quantum gravity, a yet-to-be unified theory combining quantum mechanics and general relativity, could rewrite the whole story at extreme energies. What's striking, however, is how delicately tuned everything appears. A slightly heavier Higgs boson, say 130 G instead of 125, would have placed us safely in the realm of a stable vacuum. A slightly lighter one could have made the universe catastrophically unstable from the start. The fact that our measured value is hovering right on the dividing line between these two fates has led many to wonder whether this fine balance is just coincidence or something deeper. Could this be evidence of a multiverse? In some versions of string theory, different regions of space settle into different vacuum states, each with its own physical constants. In that view, we simply live in one bubble among countless others, a pocket of reality where the Higgs field happened to fall into a metastable but long-lived state. Other bubbles might be more stable, or have already decayed. Our universe is habitable because of its instability, not in spite of it. The Higgs field, then, is both a gift and a gamble. It gives us mass, structure, and the very fabric of the visible universe. But it also sits atop an abyss we barely understand. Its mass points to a possibility that everything we know, stars, galaxies, time, even the laws of physics, rests on a temporary scaffold. A scaffold that could collapse not because of a mistake, but because that's simply the way quantum reality works. The Higgs field doesn't just explain why things are. It reminds us that they didn't have to be this way. It pulls back the curtain on a universe far more delicate, more mysterious, and more dynamic than we ever imagined. And in doing so, it leaves us with the most haunting question of all: how long does reality have left? In the classical world, certainty reigns. A ball rolls downhill, a glass shatters when dropped, and objects stay where you put them, unless something moves them. But at the subatomic level, all bets are off. Welcome to the quantum realm, where particles can pass through walls, probabilities trump certainties, and the laws of physics resemble a game of dice rather than a neatly written rulebook. At the heart of this strangeness lies a phenomenon that feels like pure magic: quantum tunneling. Imagine a particle trapped inside a box with thick walls. In classical physics, if the particle doesn't have enough energy to climb over those walls, it's stuck forever. But in quantum physics, that same particle has a chance, however small, of simply vanishing from one side of the wall and reappearing on the other without ever going over the top. It's as if reality glitches for a moment, allowing the impossible to happen. This is quantum tunneling. And while it sounds like science fiction, it's one of the most well-tested phenomena in quantum mechanics. Tunneling isn't a rare or niche event. It's a cornerstone of the quantum world. Nuclear fusion in the sun relies on it. Electrons in semiconductors tunnel through potential barriers to make modern electronics work. Even radioactive decay is powered by particles tunneling out of atomic nuclei. In the quantum universe, nothing is truly static. Everything, even the vacuum of space, is constantly in a state of jittery fluctuation, like a restless sea of uncertainty. The rules governing tunneling emerge from the wave-like nature of particles in quantum mechanics. Unlike the hard dots we imagine from high school diagrams, particles in quantum physics are described by wave functions, mathematical expressions that represent a range of probabilities for where a particle might be. A particle isn't in one place. It exists in a cloud of maybe. If part of that cloud stretches into a region normally off limits, like the other side of a barrier, there's a chance, however minuscule, that the particle will actually be found there. It's not that the particle climbs the barrier or drills through it. It simply was there all along, in a statistical sense. And now that's where it shows up. Now stretch this idea from particles to the very fabric of the universe. Imagine our universe is stuck in a false vacuum, an energy state that appears stable but isn't the true lowest energy configuration. In this scenario, our entire universe is like that particle in the box. It doesn't seem to have enough energy to move to a different state, so everything feels solid and permanent. But quantum mechanics says that's an illusion. Given enough time, the universe can tunnel into a lower energy state. Not by force, but by chance. This is the terrifying beauty of quantum tunneling. It doesn't need a reason to happen. It just needs time, The more time passes, the greater the statistical likelihood that a vacuum decay event, essentially a bubble of true vacuum, will spontaneously appear. It's not triggered by a cosmic error, an outside force, or even a fundamental instability. It's simply the universe rolling the dice again and again over trillions upon trillions of years. And one day, the roll comes up snake eyes. This isn't mere speculation. It's baked into the mathematics of quantum field theory. Every point in space is a potential launch site for such a tunneling event. And once it happens, a bubble of lower energy vacuum forms and expands outward at the speed of light, rewriting the rules of physics in its wake. Nothing can stop it. You wouldn't even see it coming. The inevitability of quantum tunneling makes our universe feel more like a temporary arrangement than a permanent home. And the longer it exists, the higher the odds it will eventually change. It's as if reality is playing Russian roulette with infinite time. The bullet is guaranteed to fire. But when? That's the cosmic mystery. It could be in 1 billion years, or 10 trillion, or it could have already started, and the light speed wave of destruction is simply on its way. What's both sobering and awe-inspiring is that quantum tunneling isn't random chaos. It's predictable randomness. We can calculate the probabilities, chart decay rates, and simulate the dynamics. But we can't pinpoint a time or location. It's like watching a volcano with no clear signs of eruption. You know it will happen. You just don't know when. Some physicists argue that quantum tunneling might explain how the universe itself began. The Big Bang could have been a tunneling event from a prior vacuum state, a sudden snap from one energy level to another, igniting the explosion that birthed time and space. If that's true, tunneling didn't just shape our future, it created our past. And yet, for all its power and weirdness, tunneling is also a deeply humbling reminder. We often think of the universe as something secure and immutable, with laws we can depend on. But quantum tunneling whispers a quieter truth. Nothing is guaranteed, not even the vacuum we live in. Every moment we exist, we do so on borrowed time granted by statistical fortune. Our continued survival is not owed by the universe. It's granted by chance. Quantum tunneling turns the cosmos into a casino where the dice never stop rolling and the stakes are absolute. And whether we like it or not, we're all playing the game. If quantum tunneling threatens the destruction of our universe, the natural question is that where it ends? What if the fallout doesn't stop here? What if the collapse of one universe is just the beginning, like knocking over the first domino in an infinite line of realities? This isn't just the stuff of comic books or speculative science fiction. It's a genuine, if speculative, idea arising from real physics that the multiverse itself could be vulnerable to the same existential glitch. To understand this possibility, we need to stretch our imagination far beyond our own cosmic bubble. The idea of a multiverse proposes that our universe is just one of many, perhaps even an infinite number, each with its own laws of physics, constants of nature, and vacuum states. Some might look a lot like ours. Others could be radically different, with different particles, forces, or even dimensions. This idea pops up in string theory, cosmic inflation, and other attempts to unify physics. In some scenarios, these universes are like bubbles floating in a vast, inflating ocean. In others, they exist side by side, partitioned by higher dimensional barriers we can't perceive. Now here's the unsettling part. If one of those universes undergoes vacuum decay, what happens next? If the laws of quantum field theory allow one universe's vacuum to collapse into a lower energy state, forming a true vacuum bubble, then that bubble could, in theory, interact with neighboring universes. And that interaction might not be polite. It could be catastrophic. In a multiverse governed by an overarching energy landscape, all universes might be sitting in different valleys, some deep and stable, others shallow and precarious. If one universe collapses to a deeper valley, the resulting vacuum bubble might not respect the boundaries between realms. It could breach the thin membranes or brains that separate universes, causing a chain reaction. One collapse could destabilize others, setting off a cosmic avalanche of vacuum decay, a multiversal domino effect. This might sound like fantasy, but it's rooted in questions physicists are seriously exploring. In some models of eternal inflation, new universes are constantly being born in a chaotic froth, each one bubbling into existence from the energy of inflation itself. These universes aren't isolated. They arise from a shared dynamic field. If that field undergoes a phase change, or if one bubble decays violently, it might influence adjacent regions. It's like popping a balloon in a room full of balloons. The shockwave could cause nearby ones to burst too. The scenario becomes even more complicated when you add quantum entanglement into the mix. Some speculative theories suggest that different universes may be quantum entangled at birth, sharing a deep connection through their initial conditions. If one universe undergoes a radical shift, like vacuum decay, it might ripple through this entangled network, subtly or catastrophically altering the fates of others. This is more metaphor than math at this stage, but it shows how deeply interconnected everything might be in the grand cosmic architecture. Let's imagine what this would mean in practice. A universe like ours tunnels into a lower energy vacuum state. Instantly, a true vacuum bubble forms and begins expanding at the speed of light, erasing the old laws of physics. But as it tears through space-time, it hits a boundary, another universe, perhaps only microns away in a hidden dimension. Does it stop? Or does it plow through, its new vacuum state overwhelming everything in its path? If the latter, then that second universe collapses too, generating its own bubble, and so on. One decay leads to another, and another, until entire chains of universes fall, like cosmic dominoes, tipping one by one in a cataclysmic cascade. What's even more chilling is that we'd never see it coming. If such a collapse started in a far-flung part of the multiverse, there'd be no signal, no warning, only the instant rewriting of physics the moment the bubble reached us. Or perhaps we wouldn't even notice. Some versions of this theory suggest that all of reality, not just a single universe, could disappear without a trace, replaced by something we cannot imagine and will never perceive. Of course, this is all deeply speculative. We don't yet have evidence for other universes, let alone the mechanism by which they might influence one another. But the mathematics behind vacuum decay doesn't stop at our cosmic doorstep. If the multiverse is real, and if it's connected by a shared energy field or fabric, then the threat may be universal in the literal sense. What this tells us is that instability may not be isolated. The cosmos could be more like a house of cards than a fortress of stone, elegantly constructed, astonishing in its diversity, but ultimately delicate. One sudden shift in the quantum vacuum, and the structure could tumble in ways we can barely begin to understand. In that sense, the multiverse isn't just a stage for countless stories. It might be a system of interlinked fates. If one chapter ends abruptly, others may follow. And in the silence that remains, no voice will be left to tell the tale. Imagine trying to detect the instant the universe decides to delete itself. No noise, no light, no warning, just the sudden redefinition of everything. That's the terrifying silent signature of vacuum decay, an event so swift and final that it's almost poetic in its violence. But for scientists probing the limits of physical reality, the silence isn't an excuse to ignore it. It's a challenge, a dare. Could we, with all our instruments and genius, see it coming? To even begin to detect vacuum decay, we first have to understand what it is we're trying to measure. The true vacuum, if it exists, would be a lower energy state of space itself. That means that detecting vacuum decay is not like spotting a meteor on a collision course. It's like trying to measure a change in the very fabric of reality before it unravels. That's a very different kind of problem. We're not looking for particles or waves. We're looking for signs that the rules governing them are starting to shift. But how? One method involves high-precision measurements of fundamental constants. If the universe is on the brink of transition, some theorists believe tiny anomalies could leak into measurable physics. For example, slight changes in the strength of the electromagnetic force or the fine structure constant could hint that the vacuum is less stable than we thought. Physicists have built incredibly sensitive devices, atomic clocks, interferometers, particle detectors, that can notice deviations on the scale of 1 part in a billion. But even that might not be enough. The problem is that vacuum decay isn't gradual. It doesn't broadcast its arrival. If it occurs, it does so via quantum tunneling, meaning the true vacuum bubble just pops into existence somewhere and expands at light speed. There's no way to detect something moving faster than your ability to receive information. If a vacuum bubble began its deadly march on the far side of the galaxy, we wouldn't know until it hit us. And by then, well, we'd already be part of the new vacuum, our atoms rewritten or erased, our concept of space and time meaningless. Still, not all hope is lost. One of the more innovative approaches doesn't focus on detection, but on understanding the risk. This is where the experimental frontiers lie. At the Large Hadron Collider, LHC scientists have been smashing particles together at nearly the speed of light, trying to understand the Higgs field, the very thing that could be tied to vacuum instability. The mass of the Higgs boson, discovered in 2012, offers clues. At about 125 GeV, it sits precariously in a zone that suggests our universe might be metastable, not quite stable, not quite doomed. That's unsettling, but it also gives physicists a foothold. If we can measure the Higgs field and its interactions with more precision, we might be able to calculate the odds of vacuum decay more reliably. Some researchers are also pushing into theoretical territory, mapping out what's called the vacuum stability phase diagram. This shows different possible fates of the universe based on the values of key parameters, like the top quark mass, Higgs boson mass, and more. If those parameters shift ever so slightly, the universe becomes either more stable or dramatically unstable. With more experimental data, we might one day refine this map and say with more certainty, we are safe or we are not. But even then, detection isn't the same as prevention. That's the haunting truth. Let's say, hypothetically, we develop a method to detect the formation of a vacuum bubble. What could we do about it? If it's traveling at the speed of light, we can't outrun it. We can't block it. We can't contain it like a chemical spill. The laws of physics themselves would be rewritten in its wake. Preventing vacuum decay is like trying to stop a mathematical equation from being solved. Once it's initiated, it's over. That said, theoretical proposals have emerged, more thought experiments than engineering plans, about altering the conditions of space to make decay less likely. Some suggest that future civilizations could manipulate fields at a cosmic scale, perhaps reinforcing the false vacuum or steering decay toward uninhabited regions. Others speculate that if we could precisely understand the quantum landscape, we might somehow patch weak spots in space-time. But again, these are the dreams of post-human intelligence, not the tasks of present-day labs. Where things get even more speculative is in the realm of simulated reality. Some physicists and philosophers entertain the idea that if we're living in a simulation, then vacuum decay is not a physics problem, but a software glitch or a scheduled system reset. In such a case, detection might come not from sensors, but from recognizing patterns or code-level anomalies. It's a fringe idea, but it underscores how desperate and imaginative the scientific community gets when faced with a phenomenon that defies traditional detection. Despite these challenges, the search continues. Every new experiment at the LHC, every refinement in quantum sensors, every slight anomaly in astronomical data might hold a clue. Space observatories now look for unexplained variations in the cosmic microwave background that might hint at other regions of space undergoing radical shifts. Earthbound labs continue to push the limits of precision, hoping to catch the whisper of instability before it becomes a scream. And maybe that's the point. Even if we can't detect vacuum decay directly, we might still infer it by mapping the quantum terrain with increasing clarity, by measuring every possible twitch in the cosmic fabric, and by facing the sobering reality that some things are bigger, faster, and more final than we can prepare for. But the pursuit itself is meaningful. In trying to detect the undetectable, we stretch human ingenuity to its limits. We refine our instruments. We unify our theories. We ask the most fundamental question of all: what kind of universe are we living in? If the answer is one poised on a quantum razor's edge, then knowing, even without escape, is a triumph of understanding. Because sometimes, chasing the invisible is the only way we illuminate what's truly real. It began not with a bang, but with a whisper, a strange behavior observed in light, something no classical law could fully explain. At the dawn of the 20th century, scientists were scratching their heads over black-body radiation and the photoelectric effect. The universe, it seemed, wasn't playing by Newton's rules. Into this confusion stepped a man who would quietly ignite a revolution: Niels Bohr. His model of the atom, with electrons jumping between discrete energy levels, was the first serious gesture toward a truth that would soon upend our entire understanding of nature. Reality, at its core, was probabilistic. Bohr's ideas were shocking at the time. Until then, the scientific world had been one of certainty, of equations that described cause and effect. But quantum mechanics asked a new question. What if nature doesn't obey certainty, but probability? What if an electron doesn't have a position until we look? This wasn't just a philosophical detour. It became the basis of the most accurate theory in the history of physics. But it didn't come without debate. The early quantum pioneers were not unified in their vision. Albert Einstein, despite having laid groundwork for quantum ideas with his explanation of the photoelectric effect, couldn't stomach their implications. His famous line, "God does not play dice with the universe," was a direct rebuke to the probabilistic chaos at the heart of quantum mechanics. Bohr, unshaken, calmly replied, "Stop telling God what to do." This philosophical battle wasn't just rhetoric, it shaped the next century of science. Quantum theory grew fast. Heisenberg's uncertainty principle, Schichter-Dinger's wave equation, Dirac's quantum fields, they weren't just mathematical curiosities. They became the scaffolding upon which modern physics was built. With these tools, scientists realized that particles could be waves, waves could behave like particles, and reality itself could be smeared across multiple probabilities until a measurement collapsed it into certainty. Quantum mechanics wasn't just a theory anymore, it was the theory. By the mid-20th century, the strange quantum zoo began to expand. Physicists found new particles, muons, neutrinos, pions. The atom was no longer a tidy solar system of protons, neutrons, and electrons. It was a seething storm of quarks, gluons, bosons, and other exotic creatures. Laboratories around the world raced to catalog them, classify them, and understand their bizarre interactions. And then came the dream. Could we create a single theory that explained everything? That dream evolved into what we now call the Standard Model, a framework that describes all known fundamental particles and their interactions, except gravity. It unified electromagnetism, the weak nuclear force, and the strong nuclear force under a quantum umbrella. The Standard Model worked. Too well, in fact. For decades, it predicted everything that experiments observed. But there was one glaring absence: the Higgs boson. It was the ghost in the machine, the missing puzzle piece that gave particles their mass. Without it, the whole model risked collapse. Enter CERN, the European Organization for Nuclear Research. Nestled on the border between France and Switzerland, CERN became the epicenter of humanity's quantum ambition. In the early 2000s, construction was completed on the Large Hadron Collider, LHC, a 17-mile ring buried underground where protons could be accelerated to near light speed and smashed together with unimaginable energy. It was the most complex machine ever built by humans, and it had a singular goal: find the Higgs. In July 2012, the world watched as scientists announced they had done it. The Higgs boson had been detected. It was the final confirmation that the Standard Model was not just a patchwork of ideas, it was a real working blueprint of the quantum world. But even in that triumph, new questions began to emerge. The mass of the Higgs, measured at around 125 GeV, was suspicious. It hinted that our universe wasn't perfectly stable. It suggested that we might be living in a false vacuum, perched on the edge of a quantum abyss. This is where the human quest turned from discovery to dread. For decades, we thought understanding the quantum world would give us control. But now, as our knowledge deepens, we see that the rules we've uncovered point to our potential erasure. That's not to say progress has stalled. On the contrary, it has only accelerated. But the tone has changed. The quest has become humbler, more reflective. We are no longer just looking for particles. We're looking for answers about our place in a possibly unstable cosmos. CERN continues to be at the forefront of that search. After discovering the Higgs, the LHC was upgraded and restarted with even higher collision energies. Scientists now probe the Higgs field's behavior, searching for signs of exotic decays, hidden symmetries, or unexpected particles that could hint at physics beyond the standard model. Supersymmetry, dark matter, extra dimensions. Each theory offers new hope and deeper risks. Meanwhile, other quantum experiments have sprouted around the globe. At Fermilab in the US, the muon G2 experiment recently delivered results that may contradict the standard model, suggesting unknown forces or particles could be influencing behavior at the quantum level. In Japan, neutrino observatories buried beneath mountains listen for the softest whispers of the universe, ghost particles that may help explain why matter exists at all. And in Canada, researchers work with ultra-cold quantum systems, condensates, lattices, and entangled states to simulate realities we cannot reach, hoping to unravel truths we cannot otherwise observe. Throughout it all, one thread binds every generation of quantum researchers: the insatiable need to know. From Bohr's chalkboard, musings, to Kern's colossal detectors, every advance has been a step toward a deeper understanding of the universe and a deeper understanding of ourselves. We've learned that the world is not deterministic. That certainty is an illusion. That observation and reality are forever entangled. And still, we press on. Why? Because this quest is not just about particles or equations. It's about our need to find meaning in a universe that doesn't owe us one. It's about peering into the void, seeing chaos, and trying to sketch out the hidden order beneath it. It's about answering the most human of questions. What is this place, and what is our fate within it? From Bohr's hesitant first steps to the thunderous collision chambers of CERN, the human quest through quantum theory is the story of a species refusing to accept the surface of reality as the whole. We cracked the atom and found a cathedral of complexity. We pushed equations and found paradoxes. We built machines that let us see the invisible. And now, standing at the edge of what we know, we face a truth both terrifying and beautiful. The more we learn, the less fixed reality becomes. And yet, we chase it. Not because we expect the universe to reassure us, but because the search itself defines us. When scientists speak of vacuum decay or the potential collapse of space-time, they are discussing physical processes grounded in mathematics and probability. But beyond the whiteboards and collider tunnels, these ideas reach much further. They touch something ancient in us, something beyond physics. The suggestion that reality itself is fragile has not just challenged scientific minds. It has unsettled artists, poets, philosophers, and theologians alike. It reshapes how we paint, how we write, how we dream. It forces us to ask, again and again, what does it mean to exist? Quantum theory, by its very nature, is paradoxical. It tells us the universe is not made of solid certainty, but of waves of potential, superpositions, and probabilities that only collapse when observed. This idea, once the domain of physicists, has infiltrated every facet of human creativity. Writers speak of the quantum self, multiple lives, unfolding in the multiverse of the mind. Filmmakers explore non-linear timelines, collapses of reality, and the weight of observation. Artists, from digital creators to abstract painters, play with space, uncertainty, and fragmentation in ways that echo the quantum world. In literature, especially, the influence is unmistakable. George Louis Borges, decades before most readers even heard of quantum physics, wrote stories that mirrored quantum paradoxes, labyrinths of infinite choices, books that contain all books, timelines that split and reconnect. Today's sci-fi authors and screenwriters have embraced these themes in works like Everything, Everywhere, All at Once, and Dark, where causality collapses and characters splinter into parallel possibilities. But even outside science fiction, the themes of quantum uncertainty, identity as a shifting wave function, meaning as something constructed only upon reflection, are everywhere. But perhaps nowhere is the cultural echo more profound than in philosophy. For centuries, philosophers debated whether the universe was deterministic or free, whether meaning was objective or subjective. The rise of quantum theory exploded that dichotomy. It suggested that determinism might be incomplete, that uncertainty is not a flaw in knowledge, but a fundamental property of nature. Reality itself does not unfold like clockwork. It unfolds like poetry, with many meanings possible until one is chosen. This, in turn, has deepened modern existential thought. If our universe is perched on a false vacuum, if it could spontaneously tunnel into a lower energy state and wipe out everything we know in a flash, we are left with a disturbing but liberating idea: nothing is promised. There is no cosmic guarantee of permanence, no underlying law that ensures our survival. This aligns with the philosophies of thinkers like Camus and Sartre, who argued that in a meaningless universe, our only duty is to create meaning. For some, that realization is terrifying. For others, it's a call to live more vividly. If the cosmos itself is uncertain, then every moment of clarity, of beauty, of connection becomes more precious. In this sense, vacuum decay theory and quantum instability are not just about doom. They are about appreciating the improbable miracle of now. Each breath we take exists because the universe still holds. That's poetry in motion. Religions, too, have felt the quantum tremor, not in the sense of direct conflict, but in the way these ideas invite reinterpretation. Some theological thinkers have embraced quantum theory as a new language to describe the ineffable. The idea that reality is non-local, that particles separated by galaxies can still influence each other instantaneously, seems almost spiritual in nature. It evokes ancient notions of interconnectedness, of oneness beneath multiplicity. In Hindu philosophy, for instance, the concept of Maya, that the visible world is an illusion hiding deeper truth, resonates with the quantum idea that what we see is just one collapsed version of many. Similarly, the Buddhist idea of impermanence finds eerie echoes in quantum instability. Everything, from the subatomic to the galactic, is in flux. There is no ground beneath our feet, only the illusion of permanence. For many, this fosters humility. If our universe can vanish without warning, due to a shift in the quantum vacuum, then our ambitions, our egos, even our civilizations, are not guaranteed legacies, but flickering sparks in a fragile system. And yet, the cultural response has not been solely one of despair. Artists, philosophers, and everyday people have used these ideas to reimagine purpose. If nothing is permanent, then everything matters. If the cosmos is random, then kindness is not required. It is chosen. And that choice becomes meaningful precisely because it is not dictated by physics. The beauty of a painting, the truth in a line of poetry, the tenderness of a quiet moment, these are not undermined by quantum theory. They are amplified by it. One of the most profound impacts has been on how we view knowledge itself. Quantum theory suggests that observation alters reality. This idea has filtered into epistemology, the study of knowledge, and shifted our view of truth. No longer is knowledge seen as a detached, objective collection of facts. It is now understood, in many circles, as participatory. We are part of what we observe. The line between subject and object blurs. This doesn't just change how we do science. It changes how we interpret history, politics, relationships. It invites empathy, humility, and responsibility. Even in popular culture, quantum echoes persist. Children's books reference multiverses. College students ponder Schrodinger's cat as a metaphor for indecision. Memes poke fun at entanglement and tunneling. While the science is often simplified or misused, the deeper cultural effect is clear. Quantum ideas have become metaphors for the modern human condition. Uncertainty, superposition, collapse, they are no longer just physical phenomena. They are emotional truths. And what of the vacuum? This seemingly empty space that might one day blink us out of existence. It has become a kind of Rorschach test. For some, it's a symbol of dread. For others, it's a mirror reflecting our deepest fears and hopes. In art installations across the world, empty space is no longer just a void. It's an invitation, a blank canvas. A reminder that absence can hold meaning too. The irony is profound. As our understanding of the universe becomes more technical, more mathematical, its cultural and philosophical echoes grow more human. We are not just atoms or waves. We are storytellers, meaning makers. When faced with a universe that might collapse in a heartbeat due to quantum tunneling, we don't just run simulations. We write poems, paint canvases, ask questions that have no answers. In this light, the human response to quantum theory is itself a quantum phenomenon, spontaneous, unpredictable, beautiful. The moment we began probing the fabric of reality, we unraveled not just equations, but ourselves. We found that beneath the layers of physics lies a pulsing truth. Reality is not static. It breathes, flickers, collapses, and regenerates, not unlike the creative process or the arc of a human life. So, while physicists calculate the odds of vacuum decay, philosophers wonder whether meaning must be grounded in permanence. While particle accelerators hum beneath mountains, musicians write symphonies about entropy. And as we stare into the quantum unknown, one thing becomes clear: we are not passive observers. We are participants in a dance that is both terrifying and transcendent. And that may be the final, most powerful echo of all. In a world without guarantees, the most radical act is to create. Not because it will last, but because it exists. The universe is fragile. It teeters on the edge of uncertainty, a cosmic cliff waiting to be undone by the slightest shift in quantum forces. Every second, the cosmos pulses with the possibility of change, change so profound that it could erase everything we know in an instant. The idea that the vacuum we live in could decay, that the very laws of physics might crumble at any moment, is both exhilarating and terrifying. But perhaps the most profound lesson we can learn from this cosmic fragility is the value of the present. In the face of a universe so tenuous, what does it mean to truly live? In many ways, humanity's long journey of exploration, both in the physical universe and the inner workings of our own minds, has always been about finding meaning in an otherwise indifferent cosmos. Throughout history, we have tried to anchor ourselves in the belief that life and existence itself holds some intrinsic purpose. Whether through religion, philosophy, or science, we've built systems of thought designed to help us understand our place in a vast, mysterious universe. But what if that very understanding is built on an illusion? The idea that the vacuum could decay at any moment, sending our universe into a chaotic end, forces us to confront the possibility that we live on a precipice with no firm ground beneath us. This brings a profound shift in perspective. If everything is temporary, if everything could collapse, then perhaps the most meaningful thing we can do is to live now. The present moment, fleeting as it is, becomes the only true certainty. Quantum mechanics already challenges the very nature of time. The famous block universe theory suggests that past, present, and future might all exist simultaneously, frozen, unchanging. This defies the way we experience time, where moments seem to flow endlessly forward. If the universe is, at its core, timeless, then what we consider now is a mere illusion. In the same way, our attachment to permanence is illusory. The present, the here and now, is all we have, and it's all we ever really will have. The fragility of the cosmos mirrors the fragility of life itself. We are, in a sense, all living on the edge. Every decision we make, every moment we experience, exists in a universe governed by probabilities, uncertainties, and quantum fluctuations. From a broader perspective, the universe doesn't care whether we live or die, whether we succeed or fail, whether we find love or solitude. But within the scope of our individual lives, these moments matter. They matter because they are all we have. Our existence is a temporary flare in the vast expanse of time, but it is a flare nonetheless, burning bright with meaning and purpose. What does it mean to live with this awareness? To know that we are not guaranteed anything, neither time nor love nor success. Some might see this realization as nihilistic, even paralyzing. But others, like the existentialists before them, might argue that it is precisely this awareness of our fragility that gives life its most profound meaning. If we know that nothing is permanent, we are freed from the tyranny of certainty. We can live fully in the moment, embracing our finite nature, choosing to create meaning where there was none. Living on the edge challenges us to reassess what matters most. In the quantum world, nothing is fixed. Everything is fluid and in flux. If we accept this as true, then perhaps we too should embrace this fluidity. What we think of as stable, our jobs, our relationships, our identities, is not as solid as we once believed. And that's okay. It is in the uncertainty, the unpredictability, that true creativity and beauty arise. Take a moment to think about how you live day to day. Are you constantly planning for a future that may never come, clinging to past memories that no longer serve you, or are you here, right now? The fragility of the universe forces us to reckon with the fact that this moment is all we can control. Tomorrow might never come. Next year may never happen. But right now, we are alive, we are here, and this is enough. In this light, living on the edge, this awareness of the cosmic fragility becomes an invitation to be present, to be conscious of each fleeting moment. There's beauty in knowing that everything could end, because it makes the now all the more valuable. This knowledge doesn't rob us of joy, it amplifies it. It makes every laugh, every hug, every experience feel more intense because we understand how precious it all is. There is also something humbling in the realization that we live in a universe that could be destroyed by forces we cannot control. The idea that vacuum decay could wipe us out at any second forces us to confront our own insignificance. But this should not lead us to despair. Rather, it should lead us to gratitude. When we are aware that everything can be undone at any moment, we are given the rare opportunity to cherish what we have, to live with intention, to appreciate the fleeting beauty of existence. In the grand scheme of the universe, nothing we do is permanent, but that doesn't diminish the importance of what we do. On the contrary, it makes every act more meaningful. The awareness of fragility also prompts a rethinking of how we treat each other. If the universe is uncertain, if our reality could disappear in the blink of an eye, then it becomes all the more important to be kind, to be compassionate, to connect with others in a meaningful way. Life is short, yes, but it is also vast. And how we treat each other, how we spend our time, is what defines the contours of our existence. In a sense, the collapse of the vacuum isn't just a scientific concept. It's a metaphor for our own personal impermanence. We all face moments of uncertainty, times when everything we know seems on the brink of collapse. But it is in those moments of fragility that we find the opportunity for growth, for transformation. The present moment, fleeting and fragile, is where everything that matters happens. It is where we experience joy, pain, love, and everything in between. And perhaps that is the greatest lesson we can learn from quantum theory, that the value of life is not in its duration, but in its depth. So, as we live on the edge of a quantum precipice, let us not shrink from the uncertainty. Instead, let us embrace it. Let us live fully in each moment, knowing that our time here is both fragile and precious. We may be living on the edge, but that edge is where life happens. And in the end, that may be the only certainty worth living for. As we've journeyed through the fragile fabric of reality, exploring the quantum uncertainties and the cosmic forces that govern our universe, one truth stands out: the present is the most precious thing we have. The universe may be on the brink of collapse, reality itself a ticking time bomb, but in this very moment, right now, we are alive. We exist. The enormity of our universe, with its vastness and complexities, may seem overwhelming, but it also offers an incredible gift: the chance to experience this fleeting moment in time. Every breath, every heartbeat is a miracle. In the chaos of quantum fluctuations and the uncertainty of cosmic events, we hold within us the ability to create meaning, to embrace the now, to live fully. We can't control the vast, incomprehensible forces that shape our universe, nor can we predict what tomorrow may bring. But we can choose to live with intention, to appreciate the beauty in the small, everyday moments that make up our existence. The quantum world may be unpredictable, but that's what makes each experience we have uniquely precious. So, take a deep breath. Look around you. This moment is yours, and it is a miracle. Embrace it. Live it fully. In the face of uncertainty, let us find peace in the knowledge that our time, however brief, is our own to shape. Let the fragility of the universe inspire us to live with purpose, to cherish the now, and to find beauty in every passing second. The universe may be fragile, but we have the power to make each moment miraculous.